we're going to take a look at a few more types of graphs for quantitative data. And so the first one we're going to look at here is called a stem and leaf plot. And stem and leaf plots are useful, but generally only for pretty small quantitative data sets. And so a lot of the times you're going to have too much data to be able to use a stem and leaf plot very effectively. So you'll see why here as we go. But the process is that in a stem and leaf plot, the very final digit, so for example in the 98 the last digit is an 8, in the 114 the last digit is a 4, so the very last digit is called the leaf, and any preceding digits are part of what we call the stem. And so if you look at a data set here, we have the heart rates for a sample of individuals after 30 minutes of exercise, and we're supposed to create a stem and leaf plot. So first thing we're going to do is we're going to pull out our minimum and our maximum values because that'll help us organize the plot. So the smallest heart rate looks like it was, I think 73, but let's make sure. Yeah, it looks like it was 73. And then the largest was 114. Remember we said that the last digit is what makes up the leaf, and any preceding digits are part of the stem. And so if we kind of divide these min and maxes this way, separating those leaves from the stem, the smallest stem we need is a 7 and the largest stem we need is an 11. And so our plot is going to look like this. We're literally going to have a column labeled stem and another one labeled leaf. And our stems need to go from 7 to 11, that's what we already said. So 7, 8, 9, 10, 11. Really, this stem of 7 represents any values that are in the 70s. Here, this stem of 8 represents any values in the 80s, 90s, 100s, and 110s. And then we're going to go through and we're going to fill in the leaves that go with each stem. We're going to do this in numerical order. So our 70s values are 73 and 79. Those are the only two in the 70s. So we're going to put the 3 first, and that represents an observation of 73. And then we're going to put the 9 next, which represents an observation of 79. And we're going to keep our leaves in nice organized columns as we go. So next we need 80s. And so the 80s we're going to have, there's an 80s, there's one, there's one. So in the 80s we need leaves of 4, 6, and 7. And again, keeping these nicely organized in columns. So that represents an 84, an 86, and an 87. In the 9s, we've got, looks like 3 values again. So we've got 93 is the smallest, 98, and then 98 again. And between 100 and 109, we've got 100 and 105. So we need a 0 and a 5. So here's our 100, here's our 105. And then in the 110s, we have a 110 and a 114. Okay, and so that would be a stem and leaf plot for that heart rate data set. One of the uses of stem and leaf plots, you'll notice if we turn this to the side, is we can fit roughly here a distribution shape to the data set. The other nice thing about it is, unlike a histogram where we just know how many are in each class, in a stem and leaf plot we know exactly what those values were. So for example, we don't just know there were 3 values in the 80s, we know they were 84, 86, and 87. So that's useful, but again, if we had a large data set, it would not be very practical to do one of these stem and leaf plots. So the next one that we're going to do is a time series graph, which is used to show how a variable that we're interested in changes over time. And so in a time series graph, we are going to plot time on the horizontal axis and our variable of interest on the vertical axis, and that is a change. Usually we've plotted our variable of interest on the horizontal axis, but not so in a time series. So again, in time series, our horizontal axis represents time, so that's going to be year. And our years are already in order here. We went from 2007 to 2015. And for the sake of having space to write on the axis there, I'm going to drop the 2000s and just give you the last two of the year. So 2007 through 2015. And then the number of wins is going to go on our vertical axis. And this is wins per season for the Arizona Cardinals. And the maximum number of wins that we had in any season was 13. So we're going to go by twos here. And then we're just going to create points and connect those points with a line. And so in 2007, we had 8 wins. In 2008, we had 9 wins. In 2009, we had 10 wins. In 2010, we dropped down to 5 wins. 2011, we were back up to 8. 2012, back down to 5. 2013, bumped up to 10. 2014, up to 11. And then 2015 was up to 13. And so if you connect those with a line, and I should be a little more careful, not a line, but line segments, right? You can try to get an overall idea if there's any pattern in the number of wins per season over time. Okay, so that would be a time series plot. And then the last one that we're going to look at is what's called a scatter plot. So this is going to be a graph that we're using when we are looking at measuring 2 variables. So everything we've done so far was 1 variable. So now we're measuring 2 variables on the same individuals. And so the data set that I picked here was for a group of students, and we looked at the students' heights versus their wingspan. And so for each individual student, we measured the student's height and then their wingspan, so from fingertip to fingertip. And so each of these columns here represents an individual student, and we again have 2 variables we measured on each student. And so when we're doing a scatter plot, we're looking for a relationship between 2 variables. We're going to plot our independent variable, which if we don't know otherwise is usually the one given to us first, but we're trying to use our independent variable to predict our dependent variable frequently in statistics. So we're going to be using height to see if that can tell us about a person's wingspan. And so height is going to go on our horizontal axis. Wingspan is going to go on our vertical axis. And we're looking for a relationship between those 2. So I'm going to give this a title. And so I put these in numerical order from height. So our smallest height was at 59 inches. So I'm going to put a break here, and I'm going to start at 58. gonna go by twos. So 60, 62, 64, 66, 68, 70, 72, 74, 76, and 78. And then we're gonna do the same exact scale on the wingspans. So 58, 60, 62, 64, 66, 68, 70, 72, 74, 76, and 78. And then once we've got our axes set up, then we're ready to just plot individual points. So each person, each student is gonna have a height and a wingspan, and where those height and wingspan meet, we're gonna put a point on our graph. So the first student there was 59 inches tall and had a 59.5 inch wingspan. The next person was 60 inches tall and had a 62.5 inch wingspan. And then we had a student 62 inches tall with a 60.25 inch wingspan. And then 63 inches tall with 61.75. And then a 64 inch tall student with a 63 inch wingspan. And then we had a 65 with 65. And then a 65 with 65.5. And then a 67.75 with a 69 inch wingspan. And then a 68 inch student with a 64.5 inch wingspan. And then on to the next row, we had a 69 inch tall student with a 66 inch wingspan. And then another 69 with 69. And then a 70 inch student with a 68.5. And then another 70 inch tall student with a 71.5. And then a 71 inch tall student with a 72 inch wingspan. A 72 inch tall student with a 74 inch wingspan. Another 72 inch tall student with a 72 inch wingspan. Another 72 inch tall student with a 70.5 inch wingspan. And then we had a 78 inch tall student with a 78 inch wingspan, so that student was particularly tall, okay? And so here we're not connecting those dots because each dot represents an individual person, but what we are going to try and get a sense of is if there appears to be some relationship between height and wingspan, and what I hope you can see is that looks roughly linear there. We're going to do some tests with linearity near the end of the course. But this should look to you like it's fairly linear, the relationship between height and wingspan. So as a person's height increases, so does their wingspan, and it looks fairly constant how those are related to one another. Okay, so that's how you would graph a scatter plot.